Welcome back, everyone, to Litmus Test. Today, we're talking about energy. Not just energy, chemical energy, and batteries. But specifically, every energy. That's silly. Let's start over. Hello, everyone. Welcome to Litmus Test. Today, what about power crystals? Because if you're playing any sort of mod on Minecraft, you're probably like, oh my gosh, I got myself a battery and a battery pack and a power crystal. Or maybe you happen to read a lot of science fiction or fantasy and you're like, oh yeah, we gotta get the power crystals so we can power the stuff to save the world. Woohoo! And that's great, wonderful even. But do they work? Well, the key idea here is energy storage and transformation. So, how can we store energy? We can store energy two ways, potential and kinetic, which is a little weird to hear, but potential energy comes in four different flavors. Gravitational, where something is about to fall. Electromagnetic, where you have two charges or two magnets and they're about to collide. Chemical, where you have some chemicals and there's some energy in there. And mechanical, or elastic energy, where you have something wound back or pulled spring or whatever, and it's about to go boing. And then you can have kinetic energy. If you had a spinning disc and it was in a vacuum, either in microgravity or just levitated somehow, then it would keep spinning at a constant velocity, meaning that it has energy stored up in it. And in theory, you could add energy to it magnetically, and you could take energy away via electromagnetic induction as well. Most kinetic energy storage mechanisms are a little silly because you lose a lot of heat or energy to heat. Which brings up the question of, now that we know how to store energy, how do we use energy? Well, believe it or not, we don't actually use chemical energy. When I say useful energy, I'm talking about electrical, mechanical, kinetic, light, sound, and heat, because that's what we actually want for all the devices that we have, for all of the things that we do. That's what we use the energy for. We convert chemical energy into these things, we convert solar energy into these things. This is what we're looking for. Electrical energy to power devices, mechanical energy to power things, light, sound, and heat for general all-purpose goodness. So, the obvious solution is we can transform energy. We can turn mechanical kinetic energy into all sorts of things, including potential, sound, electrical, heat. We can turn that electrical and heat energy into all sorts of other things, such as more heat, light, sound, more mechanical, kinetic, and even chemical, and chemical can go to electrical and heat, and they can all just go back and forth all over the place. But the total amount of energy remains constant. That's the first law of thermodynamics that we discussed in the last litmus test. And all the energy transformations involve loss as heat, meaning that you can go from electrical to heat, or you can go from electrical to light, but when you go from electrical to light, you also make heat. And when you go from mechanical kinetic to sound, you create a little bit of heat as well. So there's all of these things that lose a little bit of heat, meaning that slowly and bit by bit your machine runs down. But that's the basics of it. Take some sort of stored energy and turn it into something else useful. So what are power crystals then? Or energy packs? How do they store energy? Well, the modern day equivalent of that is known as batteries. And batteries store energy in the form of chemical energy and turn it into electrical energy and a little bit of heat. And it's generally thought that most energy packs in science fiction are thought to do the same, unless they specifically say, oh, look, it's a little nuclear energy reactor, or, ah, yes, it's exotic thermionic power fuel from the Delta Cluster, or something. Like in Star Trek, where they're using like antimatter through dilithium engine crystal. Hey, look, power somehow. Power crystals, on the other hand, are generally magical in that no one even attempts to explain. They're just like, you just plug the power crystal in and there you go, you've got magical power, yes. But the idea is similar, so let's examine it from the modern lens of batteries and see, can we extend the science of batteries to these other things? Batteries work by storing chemical energy, turning it into electrical energy, but what the heck is chemical energy? Energy is stored in chemical bonds. Duh. That's nice. How is it stored? What is it? Well, it's the energy that's needed to break a bond, or it's the energy released by forming a new bond. So if I pull two atoms apart, I've broken a bond, it's put energy into that bond to break them. On the other hand, if I let two atoms snap back together, they're going to release energy, and that amount of energy is also kinetic. There's also chemical energy. Now, when we do math and science with this stuff, we often consider it as heat, and we just pretend it's heat because it's easiest that way, and we give it a special name. We call it enthalpy, and enthalpy is not the same as heat. Enthalpy is like stored heat, kinda. It's enthalpy is probably the most pure form of energy, sort of, but yeah, not really. It's measured in joules. You can do math with it. You can add stuff up, and so you can say, well, if I take this salt and I dissolve it, it has a certain enthalpy, and then as I mix it, there's a certain enthalpy, and then when it reacts with the salt that's in solution, there's another enthalpy, and then when that salt crystallizes out, that's another enthalpy, and so the total enthalpy of the reaction is -5, and therefore I get a little bit of energy coming out, and it warms up slightly. Great, and so that's how we handle chemical energy. But what is chemical energy? It's the energy needed to break or form a bond, but how is it stored? We all understand how gravitational energy is stored. It's something's about to fall, and electrical energy is pretty simple. It's two charges that are going to run into each other, and so on. But what's chemical energy? Well, to answer that, we need to know what a chemical bond is, and a chemical bond is the interaction of the electrons of two atoms. There are three types of these chemical bonds, three ways two atoms can interact. You can have ionic, covalent, or metallic bonds. Ionic bonds are the types you see in rocks and crystals, and they consist of electrostatic attraction, meaning positive charges and negative charges that stick together. Covalent bonds are weird, and they're the entanglement of two electrons between two atoms, the idea being that two electrons get very confused, they don't know who they are anymore, and so they just decide to settle down between two atoms until they can figure it out. And metallic bonds are where all the electrons get confused, and they all don't know who each other are, and so they all wander around between all of the atoms, and they float around between metal atoms, and it becomes like a giant electron blanket or something. Blanket's not the best metaphor, but it's the one I'm going to use for this presentation, but it will make sense later. Now, the energies of these bonds is the chemical energy. So if you've got a certain amount of energy in your ionic bond, that's how much chemical energy can be stored or released from that bond. Well, ionic bonds are measured as two electrical charges, which is pretty well understood. You can just say if I have charge A a positive and charge B a negative, and I have them 1 meter apart, and I bring them together, that amount of work can be turned into energy, or I should say can be expressed as energy. Or if I have them, they're right next to each other, and I pull them 1 meter apart, I've put in a certain amount of energy by that amount of work. Pretty simple. There are other ways to formulate it as well, including integrals, but we're not going to go into that. On the other hand, there are covalent and metallic bonds, and they're weird. They have something called a wave function that tells you what their energy is, and that wave function is known by psi. So what is psi? What are wave functions? Well, if you know anything about quantum mechanics, you know that electrons are not little tiny balls. They are clouds. They are waves. And because they are waves, they say they are clouds. Imagine you have a football player and a cheerleader, and the cheerleader is very attracted to the football player, and you want them to stay apart so that they can do their jobs, right? The football player runs into people, and the cheerleader jumps up and down. They're very important jobs, and so you decide that you have to keep the cheerleader moving so that she can't run into the football player. So you put her on a bike, and she goes around and around and around the track, and she's not allowed to cross the pitch, of course. And so that's where we get the current model, not the current, the old model of the atom that everyone is so familiar with, the one where you have all the electrons going around and around and around. They're going around so that they can't touch the nucleus. But turns out that doesn't work, because what happens if you have lots of cheerleaders? They start running into each other as you get bikes everywhere. It's a mess. If you have lots of electrons, they don't want to go around anymore, and they just want to stay far apart from each other. And besides, atoms are three-dimensional, not two-dimensional, so how's that work out? It turns out that it works out like this. Take the cheerleader and vaporize her with a big ray gun. And now you have a cheer cloud, who is probably most attracted to the the center of the nucleus. The cheer cloud is going to be most attracted to the football player. And as you go farther out into the stands and away from the top of the stands, and then farther out into the parking lot, and then out onto the street, there's less and less cheer there. There's less excitement in the air, and you're not as attracted, and you're not as interested in finding out what's going on. And you're just like, oh, look, there's something going on over there. Whereas if you're in the stands, the closer you are, the more exciting it is, right? The same sort of thing. Electrons do this as well. The closer they are to the nucleus, the more likely they are to be there. Imagine the electrons are now no longer particles, but they are clouds. If you were to map out the cheer cloud around a stadium or event, you could do the same with electrons. Map out the electron cloud. And this electron cloud has a couple properties to it. It has something called a wave function, which is a mathematical equation that tells you what the shape is and everything about it. Not just the shape, but the probability, the velocity, the momentum, and blah, 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 blah. But this cloud also has a shape, and that shape is called the orbital. So electrons have these things called orbitals, which are shapes, which you've probably learned about before. Now the shape of the electron cloud, this orbital, it can have lots of different shapes. The simplest one, of course, is a sphere. And bigger, you can get bigger spheres and smaller spheres, and you can have more complex orbitals like donuts and dumbbells and funky shapes and Z's and all that stuff, and double donuts, everything. But the simplest orbital is a sphere, and the smallest, simplest sphere will have the lowest energy. If you add a second atom in there, you've changed the energy somewhat. Now, turns out that the bigger and more complicated you make your orbitals around a single atom, the more energy they take up. But when you include other atoms in there, sometimes the energy is lower than if you had them not together. If they were apart, they might have higher energy because maybe when they get together, the atoms become happier somehow. And we call that the octet rule, but that's a different subject. So bigger, more complicated orbitals generally have larger energies. This is a generalization and not very true. But for now, you could think of it as the chemical energy inside a bond is the energy of the electrons. How much energy are they going? How fast are they going? How big are they? Are they in a very strange-looking cloud, or are they in a very simple cloud? Now, the difference between covalent and metallic bonds, both of them exist in this cloud. Covalent bonds are two atoms that are stuck together, and they have their own cloud between those two atoms, and that's it. In a metallic bond, there are lots of atoms stuck together, and the cloud covers all of the atoms. Now, some covalent bonds can do weird things where they can send electrons from one bond to another, and that's, again, another subject, but the basic idea is still there. Covalent bonds are like a stick between two atoms, whereas metallic bonds are like a blanket covering lots of atoms. Now, if you want to have a chemical reaction, you've got to change the chemical bonds, and changing the chemical bond requires changing the chemical energies, because the new chemical bond is going to have a different shape of the bonds than the old chemical bond did. So you're changing the orbital, you're changing the shape of the cloud. If you go to a smaller and simpler orbital, then you're going to give off energy. And when you go to a more complicated and larger orbital, you're going to eat up more energy. And so the energy can be absorbed or released as heat, light, or electricity. When you break a bond, you eat energy, and when you form a new bond, you give off some energy, and together you'll decide whether or not you're going to give off or absorb heat, light, or electricity. In the case of batteries, we're going from two atoms that are in very separate locations, and they're going to kind of, well, they're not exactly going to combine, but they're going to combine with an electrolyte, and that is going to change the shape of the electrons, which gives us some energy. In this case, electricity with a little bit of heat. Now, like I said, heat, light, and electrical. How do they actually work? In a heat transition, you get the electron that pops off of one orbital, or it goes from one orbital on one atom to another orbital on a different atom. And when it hits that other one, it causes the other one to vibrate, because all of a sudden, if it's going to pop off of one and go to the other, that other one must be somehow more favorable. It must be more stable. It must have less energy. All that extra energy that it had start up in the big cloud, go into the small cloud, turns into heat, where it makes the atoms and molecules vibrate. That's not useful for electricity, but it could be useful for warming yourself. You can do the same thing with light, most commonly seen in fire, where an electron snaps from one orbital to another orbital on the same atom or molecule, and in doing so, it gives off the extra energy as light, a photon. And there's a little bit of vibration going on as well, so a little bit of heat. And then batteries. Batteries are where the electron leaves the atom completely, and by doing so, since there's a wire there, it pulls the entire metallic electron blanket through the electric, or via the electric field of that wire of that blanket, and that sucks up an electron on the other side. Confused? Great. Here's a picture of an electrochemical cell. On the one hand, we have something called the anode, and on the other hand, we have the cathode, and these are the positive and negative ends. And then, of course, there's an electrolyte, which helps the stuff move from one side to the other, and then there's the wire, which helps the electricity move from one side to the other. So you have to start at your anode, and the electrons will hop off of the anode, and over on the cathode, one of them will hop back onto the cathode, and they do that through the electrolyte, and they also do that through the wire, and they do it at the same time. It's not like one electron jumps off the anode, he walks over to the cathode and hops back on. And I'm sure everyone looking at that would be like, whoa, 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 that doesn't even, you wouldn't even get electricity like that. And it's true. Well, let's have some analogies. Imagine a cat food dish. When the cat eats the food bits at the bottom, there's like a little tank above it, and the cat eats and eats and eats, and then the food falls down into the bowl again, and every so often you have to refill the little tank. It's like one of those refillable food dishes things. They're really fancy. Anyways, every so often, the human has to refill the jar to keep it full. Well, as the food bits fall down, that's converting gravitational potential into kinetic. And that falling is the same as when electrons fall off of the anode. Remember, they're in a metal, so it's a giant blanket, a giant cloud of electrons. And when they fall off, they pull all of the other electrons with them just a little bit. And that pull is converting chemical energy into electrical energy. That pull is the electrical energy there. But maybe you don't like this idea of falling. Maybe it still seems a little silly. Why pull if they're just like that? Well, the answer is, if you don't like the idea of them falling through the wire, just imagine it as this pulling of a blanket. Since wires are metals, they have the metallic bonds, and as you pull on the electric field here, well, you're not really pulling one electron because all the electrons are very confused about who they are. They're not individual electrons, they're one giant electron, like a giant blanket, and you can pull the blanket. And if you put your little brother on the blanket, you can pull him around too. Well, I can put a light bulb on the blanket, and I can pull the blanket through the light bulb, and that makes the light bulb glow because I'm pushing energy through it. That's what's happening here. But maybe you still don't like this idea of pulling electrons. Let's look at it from the cathode side of point of view, where you're pushing things. If you have the cathode and you're trying to push an electron on, well, he's going to bump into another electron, and so he's going to bump into another one. And as you add an electron to the giant cloud of electrons in the wire, it's just going to send a big ripple or a big push all the way through until at the very end, on the anode, an electron pops off. And as that push goes through, it's going to go through a light bulb or something, and hey, there you go, light bulb turns on. You can imagine this as if it were a giant burrito, like a really, really, really full burrito. And you're the worker, and the customers ask for extra cheese, and you're just like, there's no more room for cheese, dude. And he's like, I want extra cheese. And so you pull out a syringe, and you stick it into the burrito, and you start just injecting more cheese into his burrito. Sooner or later, that burrito is going to burst, and stuff is going to come out the other side. And as you keep pushing stuff inside the burrito is going to move around a little bit because you're moving stuff, and that's the same thing happening in the wire. Electrons add on to the cathode, and they push all the way through and squeeze one electron out the other side. Obviously, when you stick your cheese in there in the burrito, you're not like the cheese that you push in is not the same stuff that pops out the other side. It's causing a push, and that push goes at the speed of sound. Well, the same thing happens in a wire. You're pushing something, and that push happens at the speed of light through the wire, or very nearly. So that's how a battery works, but how's that going to help us with a power crystal or any of that? And surely there are other, let's tie this all together, right? So you want to use your cell phone, and you want to use the super awesome power crystal, but you need a way to store that energy. So you go look at some chemical energy, but we're pretty much at the limit of what batteries can do, and your battery for your iPhone probably only lasts like 5 or 6 hours. So obviously the limits of what batteries can do aren't super great. Well, what about like burning stuff? You know, we burn coal and get tons of electricity out of burning coal, right? Can you have a coal-fueled plant on your phone and have it be efficient? Well, no, because imagine your fuel is like the anode of a battery, and the oxygen that you're going to burn it in is like the cathode of a battery. electrons are still going from one thing to the other. They're still going from the fuel to the oxygen, and you're burning something. Okay, so how come we can't put a wire on it and just, make it go? I mean, it sounds like it should work, right? The problem is that fuel, like wood and coal and stuff like that, generally does not conduct electricity. They're all full of covalent bonds. They're not full of metallic bonds. And the nature of metallic bonds lets you push stuff through. Covalent bonds don't let you do that for the most part. There's a few that let you push a little bit of electricity through, but for the most part they don't. Meaning that you can pull an electron off and great, you've destroyed one molecule. Or you can try squeezing an electron onto a different molecule, but it's just going to be like, whatever, I can't do anything with you. And it won't send that push all the way through the wire because there's no bond connection. The electrons are not connected in any way to each other. So instead, you just get heat and light and fire and a burn. Well, so what about energy packs? Surely there's a better way for them? Well, probably not. Energy packs are just batteries, right? If you wanted an energy pack to work, you'd have to find a way to make a better battery. And then you just call it an energy pack. You could do that through maybe harnessing the powers of lithium and fluorine, or lithium and oxygen, or if you're really good, you could find a way of getting neon to lose some electrons, and you might be able to get some electron transfer there, but unless there's some sort of exotic energy source that we haven't found yet, an energy pack is the same thing as a battery, and like the same thing, and we're pretty close to the limits of batteries. So what about a power crystal? We've talked about fuels are full of covalent compounds and bonds, and metals are full of metallic bonds. Crystals are full of ionic bonds, which have electrostatic interaction, remember? That means that they should conduct electricity, and they kind of do, but they don't. I mean, the electricity is already moved. They just allow you to move more electricity through it. They don't provide any electricity. And by pulling something, if you were able to pull off an electron from one of the atoms in an ionic compound, it wouldn't pull all the rest of them. They're not one giant electron blanket. They're individual spots of positives and negatives. The best thing you could do is if you could make a crystal that was all positive and another crystal that was all negative by taking the electrons from one crystal and moving it to the other, and then you connected them in a circuit, but a circuit with a really big switch. And so anytime you needed to use the energy, you could hit the switch and that would connect the circuit, and the electrons would flow from the negative crystal to the positive one, which would be great, except A, your battery probably wouldn't last very long, and B, it'd be very, very hard to store. Coulomb's law says that opposite charges like to attract each other, and the more powerful the charge is, the more powerful the attraction, especially if they're really close together. So you try putting two crystals, a positive and negative one, inside a little gun where they're maybe a couple inches apart. They're going to be really, really strongly attracted to each other. Even if you could have them perfectly insulated so that no electrons could flow from one to the other, which isn't going to happen, but even if it could, they would still be attracted to each other, and you'd have to hold them apart, physically hold them apart somehow as you charged and discharged it. Furthermore, you'd only be able to get half of what you would expect to get out of it, because once the two things had an equal charge, you would have no more power. You could try putting extra energy into the charged up crystal by making its electrons so fast and so energetic that they form a giant metallic electron blanket, or even going past that and making them into an anti-ion, where they're pretty much just the elements, or a plasma. But at that point, you're no longer looking at useful energy for electricity. You're looking at energy that you can get out as heat and light, because electrical energy is only given off as electrons moving through things, which means that no matter how energetic those electrons are, they're only going to move through something at a certain speed. And that extra energy, that's just going to go into stuff as heat or light. That's not going to become extra electricity for you. Though it might have a little bit of extra force, which means instead of extra energy, you might maybe have a few extra volts or a few extra amps, but you still would not have extra energy. So, alas, power crystals, as we understand physics now, are impossible. At any rate, we do still have some things because, like I said, we still have batteries. And now you know a little bit more about how batteries work. You can improve the energy of batteries by doing all sorts of really nifty things with them, changing their geometry, changing their shape, making them more efficient, getting better elemental pairs so that you can get the maximum possible energy out. And perhaps someday in the future we'll find materials that can allow for some really unique and very strange, maybe some energy transformations that happen in steps. These are all chemical reactions, of course, so power of chemistry. Get to it. Anyways, thanks for watching. If you had a great time, please like and share, and I'll see you next time. Remember, don't catch on fire.